Okay, here's another example of a two-dimensional collision. In this problem, marksman and trick shot artist Kristen Joy Weiss is going to fire a 13-gram bullet at a 12-gram quarter that's thrown straight up in the air. Kristen fires her. That's her rifle. Her rifle at a 45-degree angle to the horizontal. And then fires the bullet with a speed of 650 meters per second. Just as that coin hits the highest point, the bullet hits it and glances off, giving the coin an exactly vertical upward velocity of 130 meters per second. At what angle, measured with respect to the horizontal, does the bullet ricochet away from the collision? Well, good habit is always have a before and after picture. And before is like right before the event of interest, which is the collision between the bullet and the coin. So it says here that coin is at its highest point. That is where its velocity is going to be 0 since it was tossed straight up. So there's some key information there that isn't given numerically. So at that before instance, right before it's going to hit, our coin is just sitting there. Velocity of the coin is 0. And our bullet is moving that way. After, we know, I'm going to orient it, that the coin is now going here. The velocity of the coin final is straight up. And I think I can ascertain here that the bullet is going to keep going right. We have some rightward momentum at the beginning and no rightward described yet, so we have to maintain that rightward momentum. It's got up. It's about the same mass. It's going much faster, so there's probably still some more up. And this is a guess, but I think it's a pretty good one, that the bullet is going to still be going up, but not as much. Velocity of the bullet final. But I'm going to need to determine that x and y components. So to do that, I need to select an axis system for this. And a traditional vertical horizontal is going to work for us since we've got some vertical velocities and horizontal angles given to us, or angles relative to the horizontal. So in both cases, we're going to use a traditional horizontal vertical axis system to analyze these angles. Now in momentum, it's a vector. Direction matters. That's why we got to break it into components to analyze it. And so then we can only really do the algebra in the x direction and then in the y direction. So if we look at the x direction first, sum of the momentums initially in the x direction is going to be the sum of the momentums finally in the x direction. What we got going initially is just this bullet. I'm going to write them both down. The system is the momentum of the bullet initial x and the momentum of the coin initial x. But we know that coin is 0 since it was straight up at its highest point. Its velocity is 0 and therefore its momentum is 0. Afterwards, we'll have the momentum of the bullet finally in the x direction and the momentum of the coin finally in the x direction. And again, from our reading, we know that the coin is going exactly vertically upward. It's not going to have any x afterwards either. So we know that's not going to be there afterwards. So it's just mass of the bullet, velocity of the bullet initially in the x direction will equal the mass of the bullet times the velocity of the bullet finally in the x direction. That's because momentum is mass times velocity. So we got to find that Vx and Vy. We know the velocity of the bullet initially is 650. We know the angle that it's at is 45 degrees above the horizontal. That way. So the x component is this part right here. That's our x, and then that'll be our y. So that's adjacent to that 45-degree angle. So the velocity of the bullet x initially is 650 cosine 45. Plug that into our calculators, and we get 459.6.62, we'll say. 459.62. Now, while we're at that, we're going to need the y. So why not find the y velocity too? The velocity of the bullet initially, y, would be 650 sine 45. Now, sine and cosine are the same when the angle is 45 degrees. So I know that that's also going to be 459.62. And that's meters per second, and this is to the right, and this is up, which are both positive. All right, so, well here, going back to the x momentums, I found this x velocity. The bullet mass is 13, but it's on both sides, so that reduces. So I can see here that the initial velocity, the 459.62, is going to equal the velocity of bullet finally in the x direction. So I got the x component. Now I have to go to find the y component. So same application. The momentums initially in the y, all added up, are going to equal the sum of the momentums finally in that y direction. So my y's initial, I have to consider the bullet y initial and the coin initial y. But again, we know that y was at rest, so it doesn't have any momentum initially. Not a plus now. That's going to equal our momentum of the bullet finally in that y direction and our momentum of the coin finally in that y direction. So here we got mass of the bullet, velocity of the bullet initially in the y is going to equal mass of the bullet, velocity of the bullet finally in that y, plus mass of the coin, velocity of the coin finally in the y. Okay, nothing really cancels out here. So we want to find this, and I think we know all this other information. Yes, we do. So the bullet's mass is 13. We can leave everything as grams. All the masses should have the same unit, and then they'll cancel out nicely. There's no need to convert unless you're asked to. And the velocities need to be all the same units, and they are, so that's going to be okay. So we can use 13 grams. That y velocity is over here, 459.62. And that's going to equal 13 times the velocity of that bullet in the y direction. Finally, I'm going to drop the final because that's the only thing left. And the mass of the coin is 12 grams, and its velocity is entirely in the y direction, vertically straight up of 130, so that's a positive 130. And plug this all in your calculator, and we get that the velocity of the bullet that's final in the y direction is going to be a positive 339.62 meters per second. And you'd multiply these here, multiply those there, subtract that over, divide by 13. The algebra is pretty straightforward to get this. Now that's my x and y's. I want to know the speed or the velocity. I want to know the angle. So is what this is asking for. I'm also going to find the speed. Now the angle, we know that that bullet has an x here. It's got a vx to the right. It's got a y that's up. So we want to find this angle here relative to the horizontal. That's what it wants. So that angle is going to equal the inverse tangent of the opposite side, the y, the vy final, over the vx. It's not always y over x. It is always opposite over adjacent. So inverse tangent of 339.62 over 459.62. Interesting that those both end in 62. And when we do that, we get 36 degrees. Theta is 36 degrees. And that's above the horizontal. Now to find the actual speed of it, which you'll have to do in other problems, the velocity, or the magnitude of the velocity, is the horizontal component squared plus the vertical component squared, square root. So when we do that, we do the doesn't really matter the order, but 459.6 squared plus the 339.6. We'll drop the 2 because of space there, squared. Carried out in the calculation. So, and when I calculate that out, I get 571.48 meters per second. We've got 2 significant digits, so 570 meters per second is good enough for that. So there you go. Another example of two-dimensional collision using conservation of momentum. Hope that helped.